Hello everyone, this is the second um, video about chapter 3. Last time we stopped at the big picture regarding the shingling. Today we're going on to talking about the details of each phrase about in the shingling. Now the first one. The task of shingling is to convert document into individual data sets. As we know, the most effective way to represent document as sets for the purpose of identifying lexically similar documents is to reconstruct from document the set of short strings that appear within it. If we do so, then documents that share pieces as short as sentences or phrases will have many common elements in this set, even if those sentences appear in different orders or phrases appear in different orders in two documents. So this section will introducing the simplest and the most common approach, shingling, as well as an interesting variation. To be simple, each document can be treated as a set of the words appears in the document, and also a document can also be represented with a set of important words. Now, with the representation of important words, this might not be the very effective method for this task. So the reason why we will left to the real explanations. Now here we are trying to using a different way, using the shingles to represent documents, to another effective conversion of documents. First, shall we look at what is shingles? Okay. Since we know a document is a string of characters, so we can define k shingles for a document to be any substring of length k found within the documents. Then we may associate with each document with a set of k shingles that appear one or more times within these documents. For example, if we treat k like 2, document D is D1 is like a very short string like A, B, C, B. So the set of k shingles will represent as SD1 can be represented with AB, BC, CA, and at last, because the last two AB is a replicate as the first AB, so in a words back, it can be replaced with AB as well. So the AB only appears once. Okay, so shingles we can think about the shingles like a bag of k length subset of these strings. Note that the substring AB appears twice within the D, but appears only once as a shingle. So a variation of shingle produces a bag rather than a set. So each shingle would appear in the result as many times as it appears in the document. However, we are not using the bags of shingle here. There are also some other options regarding how to treat white space, like blank tab, new line, etc. It very probably makes sense to replace any sequence of one or more white space characters by a single blank. This way, we distinguish singles that cover two or more words from those that do not. This example gives us an illustration of k equals 2. Actually, we know that k should be more than 2. The 2 is a very simple illustration for illustration purposes. And also we can use k, for example, maybe 5, 7, 9, but to for longer text strings. And another very important issue about how can we choose the shingle size, whether the shingle size should be 1, 2, 3, 4, 5, or 7, or 9, or whatever. But the k, theoretically, the k can be any constant as we like. However, if we pick k too small, then we would expect more sequences of k characters to appear in the most documents, so that the bag contains too many shingles. If so, we also have documents whose shingle sets has a high J-card similarities, yet the document have none of the same sentences or even phrases. Okay, so as an extreme example, if we use k equals 1, the most web pages will have most of the common characters, and a few other characters will be considered in the task of comparison of all web pages. Okay, so anyway, how large a k should be it really depends on how long typical documents here and how large the set of typical characters. One important thing we should bear in mind is that k should be picked large enough that the probability of any given shingle appearing in any given document is low. Thus, if the corpus of document is emails, we would advise picking k equals to 5 would be okay. Why? Suppose the only letters and a general white space characters appear in emails. Although in practice, most of the printable ASCII characters can be expected to appear occasionally. If so, then there would be 27 with power 5 possible shingles. Since the typical email is much smaller than 14 million characters long, so we would expect 5 equals to 5 to work well, and indeed it does. However, the calculation is a bit more subtle. Surely more than 27 characters appear in emails. However, all characters do not appear with equal probability. So common letters and blanks dominate. Okay. So instead of using substreams directly as shingles, we can pick a hash function that maps strings of length k to some number of buckets and treat the resulting bucket number as a shingle. So in this case, the set representing a document is then the set of integers that bucket number is one or more k shingles that appearing in the document. Okay, so this is a kind of manner for compressing singles with integers. And also the similarity between different documents can also be measured with the similarity matrix for the shingles. For example, the document D1 has a set of its shingles like C1. Equivalently, each document can be represented with 0 and 1 vectors in the space of K shingles. So each unique shingle is a dimension. Each single is a unique dimension, and the vectors are very sparse. So a natural similarity measure, if we using the J-CAR similarity, can be computed with in the following figures. This figure presents that the similarity between D1 and D2 is 4/8. That equals 0.5. So about comparison, based on the working assumption is that documents that have lots of shingles in common, they have similar text, even if the text appears in different orders. So the conveit that suggesting the size of K, the K should be large enough, not 1, not 2. So so that to keep most single documents should have most shingles. As experimental experience, the K equals to 5 is okay, and for short documents like emails and messages for general communications, as we discussed before. And if we try to deal with longer documentation, maybe some novel or academic articles, K equals to 10 may be better in these processing scenarios. As we know that sets of shingles are large, even if we can hash them into digits or bytes for each shingles, but the space needed to store a whole set is still roughly a couple times of the space taken by the document. If we have millions of documents to be processed in the meantime, it may not be able to store all the shingle sites hashing numbers in the main memory. So the goal of main hashing is try to replace the large sites by much smaller representation called signatures. The important property need for the signature is that we should be able to using these signatures to compare two sets and estimate the J-CAR similarity of the underlying sets from the signatures alone. It's not possible that the signatures gives the exact similarity of the sets they represent, but the estimates this will estimate they provide are close, and the larger the signatures, the more accurate the estimation is. For example, if we try to replace the 20,000 byte hash single sets that are derived from 50,000 byte documents by signature of 1,000 bytes, we can usually get within a few percent. So the motivation for main hashing, we can illustrate with this an example. Suppose we need to compare 1 million documents to find the near duplicate documents. Naively, we would have to compare pairwise, which means pair by pair, with J-CAR similarity for every pair of documents. So the comparisons carried out would be the composition of 2. So the number would be exceeds 5 times of 10 with power 11, and for estimation it will it's about 10 powers 5 seconds a day, and if we can carry out 10 powers 6 comparison per second, this comparison will be accomplished within 5 days. So if the n is 10 million, I will assume it will takes more than a year to accomplish such a comparison. So as we know that this is very time consuming and very impractical. Now we move on to the main hashing stage. To the final result is trying to produce the signature to like short integer vectors to represent the set and to also to reflect their similarities. As we know, many similarity problems can be formalized for searching the subsets that have significant intersections and based on their unions. So if we try to encode sets with bits, vectors, so 1 dimension per element is a universal set. If we can interpret such set intersection as bitwise and set the union as bitwise OR, in that case the comparison will be implemented in the vector level. For example, if we treat C1 like 10111 and C2 equals 1011, so the size of intersection, which means both bits, both have the bits equals 1, that is the first part, the first digits, and also the last 2 digits of C1 equals to the first digits of C1, C2, and the last 2 digits of C2. So the intersection is equals to 3, while the union present all the digits, either C1 or C2, they have digits like 1. For example, the first digits, not the 2, not the second, and the third, the fourth, and the fifth of the non-zero digits. So the union is 4. So in the J-card similarity, what we got is 3 of 4. Well, the distance is defined like 1 minus the J-card similarity is 1 of 4. Based on this scenario, we can use to build up such sets to based on the document and all columns of the singles. Okay. For example, if we have this document here, and the document, for example, is composed with 3 vectors, represent with columns, and each rows represent the elements like shingles. Okay. So if we try to compare document 1 with document 2 with the applicable methodology is that we can try to compare the shingles they have in common. Okay, so the one in each row and the column, if S has a number of S, okay, which means that for example, in the document 1 here, if it contains a single 1, so here is a mark of 1. Otherwise, it's a 0 here. So in this case, the column similarity is a J-card similarity in the corresponding sets. Okay. Generally, we will understand that this matrix is a very sparse, which means not so many ones will appear in this matrix. So based on this instance, how can we compare the similarity between document 1 and document 2? For example, if we try to compare the similarity of C1 and C2, so the size of intersection, which means that both C1 and C2 are represent with present one is that the this row, the row 1, the row 2, and the row 3, these are intersections. Both C1 and C2 are ones. Well, the union is that either C1 and C2 they have ones. That's the row 1, row 2, row 3, row 5, row 6, and row 7. So we have total 6 rows has either C1 and C2 have ones. So in that case, the union is 6. Based on the computation, the J-card similarity is 3 of 6, and the distance is 1 minus the J-card similarity based on these instances. It's important to remember that this characteristics matrix is unlikely to be the way the data is stored, but it's useful as a way to visualize the data. For one reason, not to store the data as a matrix, because these matrices are almost very sparse, as we mentioned before, which means that we have so many zeros, much more than ones in practice. It saves space to represent a sparse matrix of zeros and ones by the position in which the ones appear. For another reason is that the data is usually stored in some other format for other purposes. As an example, if rows are products or merchandise and columns are customers, represented by the set of products they bought, then the data could really appear in the database table of purchases. A tuple in this table would list the item and the purchaser and probably other details about the purchase, such as the data and the credit card used. This matrix can also be used to finding similar columns. For example, document to be represented by singles. Each set can be represented as Boolean vectors in this matrix. So the next goal is how can we find the similar columns? Well, we computing with smaller signatures. So in that case, we try to build up the equation between the similarity of columns and the similarity of the signatures. Now, when we finding try to find the smaller signatures, the naive approach is that we can figure out the signatures of columns. For example, we can using a small summaries of columns to represent like the signature of each column, and the second thought is that we try to examine the pairs of signatures to find similar columns. The essential part of this is that the similarity of signature and columns should be related in this matrix. One option we would think about that we need to check that columns within similar signatures are really similar. Okay, this is a very naive thought and simple thought. We should be aware of that when we comparing all the pairs that may actually take too much time. If we check out the comparisons of the pair comparisons, this method can produce false negatives and even false positives to increase the computation cost. Since the naive method is not so practical, so we are thinking about hashing columns into its own signature, though. So the hashing results is the signatures. The key idea is that if we can hash each column C to a smaller signature, represent like HC, so that HC is small enough that the signature fits in the RAM, and while the similarity of C1 and C2 can still be kept the same as the similarity of the signature of when we compare the HC1 and the HC2. So the goal is very clear that if we can find such a hash function H, so that you can meet the requirement if the similarity of C1 and C2 is high, and then we still get the high probability of HC1 to HC2. If the similarity of C1 and C2 is low, we cannot have the high probability between the HC1 equals to HC2. So the final target that we can hash documents into many buckets. We could expect the most frequently pairs of all of near duplicate documents hashed into the same buckets. So how can I find the hash functions? Okay, let's bear the goal of the man-hashing to find the hash function for implement the similarity comparisons. Clearly, this potential hash function really depends on the similarity matrix in the previous slides. Not all the similarity matrix has a suitable hash function. This is for true. So searching is a very hard job to be done. There is also a suitable hash function for the J-card similarity, which means that depends on different similarity measures, there may exist different hash functions. For the J-card similarity, this hash function is called the mean hashing. The mean hashing is that if we can imagine the rows, guys, please imagine the matrix in your brain. Imagine rows of the Boolean matrix permuted under random permutation pi. If we define the hash function is the index of the first in the permuted order pi row in which column C has the value 1. So this hash function can be represented with h pi c equals mean pi c. The mean means the first column appears the value 1. The first appears means the row number is the minimal. So this is the mean coming from. So in this case, we can use several independent hash functions to create a signature of a column in this purposes. Now, let's see an example for better understanding how the main hashing takes into events. In this example, the main hashing trying to find out the smallest colon numbers for this function. Okay, for example, in this row, the ones have 2, and also as a 1 here. So the smallest number is 2. That's the 2 coming from. Okay, and also in this row, all the ones has 7, 6, 1. So the smallest index is 1. So that's the 1 coming from. Okay, so as to these two, if we go straight to this column, all the ones happens at 2, 5, 4. So the minimum number is 2. That's the 2 coming from. Okay, if we go to see the 4 here, the 4 goes to all the third columns. The third columns is that 1, 1, 1. So the minimum number of 4, 7, 5 is 4. So this is how the 4 coming from. In that case, all the permutation we got from based on this matrix, we got the signature matrix as M here. Okay, that's the transformation mechanism regarding the hashing, mean hashing functions. Okay. Another way that we also can, another equivalent way is to store the row index here. Is that, for example, the 1, the 2 is what we got in the permutation happens in the 1. So because this one actually resides in the row 1, so that's the 1 coming from. Okay. As to this column, as to this column here, the minimum number of ones occupies 1, 6, 7. So the 1 resides in the column 5. In the row 5. So that's the row. That's the number 5 coming from. Similarly, we also get the 1 here. The 1 means that this 1 we got from the minimum number between 2, 5, 4. That's corresponding to the 1, 1, 1. So this 1 resides in the row 1 as well. So that's the 1 stands for. Add to the 1 here, because the 4 is the minimum hashing result of the 4, 7, 5. The 4 resides in the row 1, so that's the 1 coming from. Okay, so this is the function of main hashing and example here. So the reason is that why we using the main hashing to indicate the similarity between the properties is based on the following main hashing property. Suppose if we choose a random permutation like pi, we need to prove that with any permutation hash function, the similarity between column 1 C1 and column 2 C2 are equivalent to the probability that the hashed results has similar probabilities. Okay, so the reason is that if we let X to be a documentation which is composed with a set of shingles, okay, and Y belongs to the X is a randomly single, then the probability that the Y would be chosen to represent the minimum value of X is that 1 divided by the absolute x. It's equivalent. It is equally like that any y belongs to the x is mapped to the minimum element. So if we let y to be the permutation y, like the minimum permutation of C1 union with C2, then either pi y is the minimum of pi C1. If y belongs to C1, also the same principle applies to the y on the collection of C2 as well. So with this probability that both are true, if the probability that the y belongs to the C1 intersection with C2. So in that case, we can understand the probability that with the permutation on C1 equals to the permutation on C2 equals to the C1 intersection with C2 divided by the C1 and the union with C2. So this number is the same value of the C1 and C2, which proves that the similarity of the signature matrix is equivalent to the original similarity of any two columns. So given any column C1 and C2, we can get 4 different types of rows. Like A, B, C, D, like 1, 1, 1, 2, 0, 1, and 0, 0. If we're using the A to present the number of rows of type A, so the similarity of C1 and C2 are equivalent to the A divided by the sum up of A, B, C. So then the probability of hashing C1 equal to hashing C2 equals to the similarity between C1 and C2. If we look down the columns of C1 and C2, then we'll see a 1. So if it's a type A now, so then it's like HC1 equals to HC2. If it's type B and type 0, then it's not. Okay, so this is a further explanation regarding the signature matrix of the C1 and C2. So because as we have proved the similarity of signatures are equivalent to the similarity of any original columns, so if we can generalize this conclusion to multiple hash functions, so we got the conclusion that the similarity of two signatures is a fraction of the hash function in which they agree with. Because of the main hash property, the signature of columns is the same as the expected similarity of their signatures as well. Okay, so with this property, we go back to this example to calculate the similarity between the different columns and the different signatures. Okay, for example, if we try to compare the 1 and the 3, if we compare the columns here, we got 1, 1, 1, 1, 1, and 1, 1. Okay, so actually we have 3 intersection between the column 1 and column 3, and also the union is about 1, 1, 1 is 4. So the similarity between column 1 and column 3 is 4 divided by 4. That's 0.75 coming from. Okay. Similarly, we can get the column 2, with column 4 is that we got the intersection with 1 1 1 1 1 1, okay, and the unions we will also including the row 2. So that's still 3 out of 4. We got 0.75 here. Okay, it's very easier to we can get the similarity between 1, 2, and 3, 2 are zeros. If we check out the signature here, if we check about this is the column 1 and the column 3, we got 2, 2 are similar, 1, 1 are similar, so that's 3 out of, that's 2 out of 3, that is 2 divided by 3 here. And if we check out with column 2 and 4, that's 2 and 4, these two are totally identical, so that's we got the similarity about 1 here. Okay, based on this example, we can easily understand the mini hashing signatures here. It's already realized the compression functions. Okay, so if we pick like k equals to 100 random permutation of the rows, we can also think about the signature of column as a column vector. So the signature of any column will be produced according to the ith permutation. The index of this is the first row that has a 1 in column C1 in column C. Okay, so this is a similar presentation in the previous slides as well. Please note that the sketch called the signature of this column is much smaller, roughly about 100 bytes. Okay, so the compression function has been done. On this slide, this is the including the implementation tricks regarding the permutation and calculation in the one pass implementation, and I would advise students to read through after these lectures. Okay, so I believe this is the second part of regarding the chapter 3. Okay, that's good for today. Thank you. And the last part of the third part of regarding the chapter 3 will start from the slide 44.